Okay, let's come back and move on to see where we can go today. Okay, all right. Oh. Okay, almost for dinner, right? It's very late. Okay, so let's look at the descriptive statistics. Okay, and actually, simply say that the descriptive statistics you use to describe the data set. So I think most of the tools for data analysis, in the very beginning, they will let you play around with the data set, and you can, I think they allow you to work on some statistics over the data set. Okay, so we will use the descriptive statistics to describe the data set. In addition to that, we can try to have some ideas about our data set using the descriptive statistics. So whenever you have a data set and you would like to analyze them, you can try to have some simple statistics to look at the data set before advanced analysis. Okay, so for I think you have learned this kind of descriptive statistics before, like the aggregation, for example, the average, the mean, and minima or maxima, okay, something like that. That belongs to what we call like the descriptive statistics. Okay. All right, so we may use that to have initial analysis on the data set we have, and we can use that to describe our data set. And you may have some new findings after you look at some statistics to that data set. Okay, so we usually say the aggregates like the minima or maxima or the mean or average or the count or the summation, that belongs to the aggregates. Okay, that will be the statistics. All right, so there are two, in the following, I think we talk about two major types of the descriptive statistics. One would be the central tendency measures. Okay, they try to measure the center of the data set. Okay, they try to measure that, and the other one would be the variation, or we say the variability measures. They try to describe the distribution of the data, or how far the data from its center. Okay, so let's talk about these two types of statistics, or we say the aggregates. All right, so the first, we talk about the central tendency measures. Okay, we also call it like the centrality measure. Okay, the first one would be the mean, arithmetic mean. Okay, this is very common. I think you might have learned this when you are in high school. Okay, we just do a summation over all possible values and divide it by the number of observations. Okay, that would be the average or the mean. Okay, so the formula like this. Sometimes we use this mu as the mean of the data set. Use the mu to denote the means of the data set. Okay, I think this is very common, and I think everyone has known this. All right. Okay, and for the means, sometimes it's very useful when the data, when the distribution of the data set is symmetric. Okay, and without the outliers. That means we do not have some data items far from its center. Okay, the outlier says that it would be a very different data items in the data set. Okay, so that could be the outliers. So if your data set does not have the outliers and the distribution of your data items is symmetric, the mean would be very meaningful. Okay. Right. Okay, so this will be the mean. This will be the mean. And the other centrality measures would be the geometric mean. Okay, that's different from the arithmetic mean. Okay, you would take the nth root if we have the n values. We just multiply them together and take the nth root. Take the nth root of the production. Okay. All right. So this will be the geometric mean. Geometric mean, and I think we have learned these properties, right? If you remember, the geometric mean is always less than or equal to the arithmetic mean. Okay. Is that right? Something like less than or equal to. It's just, I think you have learned this when you was young. Okay. All right. Anyway, so this kind of means would be the geometric mean. Geometric mean. And the geometric mean is very useful for the ratios. For the ratios, like 1/2, 2/1, 1/2. If we would like to take the average of these two numbers, okay. If we use general means, arithmetic means, the mean of it would be 1.25, right? Equal to 2 plus 1/2 divided by 2. Okay? So this would be the general means, arithmetic mean for these two ratios. Okay, but if you take the geometric mean, that would be equal to 1. Equal to 1, okay. So for the geometric means, we usually use geometric mean for ratios. Okay. Because the distribution for the values about the ratio would be different. Okay. If you look at the line for the real number, right? So here would be 1/2, and 2 would be here. So within this period, we have lots of numbers, smaller than 1, greater than 0. And lots of numbers distributed along this line. So we have a limited space for lots of numbers. Okay. So for the ratios, we usually use geometric mean instead of the arithmetic mean. Okay. Or you can take the log. You might see the reason why. Okay. We might see that later, maybe later in this course. Okay. Another thing about the geometric mean is it is very sensitive to the values near 0. Okay. What I mean to indicate here, okay, for this part. Okay. Okay, this will be the geometric mean. Okay, we usually use that for ratios. Okay, another, we have known the means, arithmetic means, and geometric means. We might have the median, okay. The median just the middle ones among the data set, okay. Just the middle ones, okay. it depends on the number of data items is even or odds. Okay, I think you know this, right? Okay. In many real practice or in many real applications, we might prefer using median instead of the mean. For example, the distribution of the wealth or incomes. If we like to see the distribution of the personal wealth or personal incomes, we generally will use median instead of mean, okay? Because the distribution is pretty skewed. It's pretty skewed. So in that case, we would like to see which one is in the middle instead of the average. Okay. Okay. So the median is usually used for the skewed distribution, like personal wealth or personal income. We only have very, very few Bill Gates, right? But we have a lot of poor, like me, right? Okay. So in that case, if we take the average, you cannot see the real story about the distribution. So sometimes you will see the median, the middle one, or the quarter one, or three-quarter one. Okay. All right. So we might talk more when we introduce the distributions. Okay, the last centrality measure would be the mode. I think we seldom use this. Okay, the mode is the most frequent element in the data set. Okay, so in our example, if we look at the distributions of the random variables, okay, this value 6 will be the mode of the data set, because it happens most frequently. Okay. So the mode here, I think we seldom use that, right? The mode is the most frequent element in the data set. So in our example, 6. The random variable is equal to 6. Not random variable. If we consider the total number of credits used is 6, will be the mode. Will be the mode because it happens frequently, most frequently. Okay. All right. So, but it depends. Because the modes may not close to the center. The mode may not close to the center. But in our example, it could be, but in many cases, the mode may be far from the center. Okay, so here just say that you can consider different centrality measures. It depends on your the applications or the distribution of your data set. Okay, so that's why we need to play around with our data set. So whenever you have a new data set, you can try to look at their mean, their geometric means or the mode or whatever. You can check the statistics about your data set. Then you can have some idea or some understanding about your data set. Okay. All right, so this is about the centrality measures. And after we know where is the center of the data set, we might look at the distribution of the data set. Okay, that would be the job of the variance. Okay, it would just describe. It describes the how the data items are distributed. Okay, maybe around the center. Okay, so this so there are two things we can describe our data set. One is we can use its center. Okay, we can describe the center of the data set. The second part is we would like to see how the distributions looks like. We can use the variance, get the variance. Okay, so there are two you might see these two terms. They just take the square or not. Okay, a square root or not. Okay, so if we measure the sum of the squares of the difference between the individual elements and the mean, okay, and divide it by n minus 1 or n, whatever. And if we take this amount, use this amount, and then take the square root of it, we'll derive the standard deviation. Okay, it just measure how far for each element to the center. Okay, so you might have the idea about if the standard deviation is large, you might see maybe lots of the data items are far from the center. Okay, so it's just a kind of description about the distribution of your data set, the data items. Okay, so if you do not take the square root of it, it actually would be the variance. Okay, and this is a general question. We'll divide the amount by n or n minus 1, but I think it depends, right? But we usually use n minus 1 for sampling, because for the sampling we usually has at least 2 data items. Okay, and divided by n or n minus 1, well, it doesn't matter, because when n is large enough, okay, the amount can be, this will not be a big deal, okay. But in general, we'll use n minus 1. Okay, this will be the definition for the variance and the standard deviation. Okay, so and so this just give you an idea about why we need the variance. If you look at these two distribution, okay, this will be the life of the light bulb. I write it. The life of light bulbs. Okay, so for the left plot, you will say that the average lifespan for the light bulb would be 3,000 hours. 3,000 hours. So some light bulbs can live longer, but some of them will die earlier. Okay, but the average would be 3,000 hours. Okay, so the plot on the right says that the average still to be 3,000 hours. Okay, but for the right one, it says that almost every light bulb live 3,000 hours. This one, okay, that means for every light bulb will die at 3,000 hours. Okay, but here, we have a larger variance that says some of them will live longer and some of them will die earlier. Okay, so that's just illustrate the variance. Okay, the variance. It can give us an idea how the data set looks like. Okay, but similar to the means, the variance is very sensitive to the outliers, because if you look at the equation here, if we have some bizarre data item, we might have some large amount on the numerators. Okay, so that causes a large variance. So if we have more outliers, the variance could be large. Okay, so this would be very sensitive to the outliers. Okay. All right. So even though even though we have the same phenomena, if we observe, the result could be different. Still can be different. Okay. In some observation, we might have a little bit larger amount or large measure, or in some observation, we have a less amount or less measures. That depends, right? That depends. So the same phenomena do not always produce the same results. Okay, that's because we might have the variance. Okay, or we might have the errors that will produce the phenomena. Okay, if you observe some phenomena, the measure you get, the result you get may not be always the same. You might have some errors or some variance inside. Okay, so it could be the errors, or it could be the error, or it could be noise. Could be noise. All right, so so this makes things more complicated. Okay, if we just look at the variance simply, we might interpret things in a wrong way. Okay, so we don't know why we have such variance. It's very difficult to check. Okay, sometimes it's from the error, sometimes from the noise. Okay, so but we would like to see the real impact for the variance. Okay, and we would like to see the real signal, not the noise. But sometimes, in general, it is not easy to do that. We cannot tell the noise from the real signal. Okay, so yeah, so sometimes you're very frustrated because things are not what we think, right? So even though we see the results, and even though for the same phenomena, we have different observations, okay? Right. Here just have some examples saying that, okay, for the stock market, sport performance, and model performance. I just go over it then quickly. For the stock market, if you have some stocks, and if you notice the stock market, we have different, this will be the case that you think about that. We have a lot of manager that can help you to do the investment, right? And these managers will have the same training before they can help you, right? So for their ability, for the managers could be the same. Right? So if we think this straightforward, the outcomes will be the same for every manager, right? But some managers will perform well, but some will perform not well. But the reason is we don't know why. Because every manager will have the same training. Okay? They should have the similar ability, but the performance will be very different, right? This is hard to capture, right? Or you can see the sports. The sports, we have different players. But you might see this player plays or performs very well in this season, but performs bad in the following season. We have the same player, right? But why the performances are so different? So there could be many reasons inside, but it's very hard to capture that. Okay, we do not know the real reasons. Okay, or maybe the reason we think could just be a noise, not the signal. So it's not easy to tell, right? Not easy to tell. But we can use the variance to look at something. But if you want to look at more detailed insights, it could be very hard. It could be very hard. All right, so this would be about the models, because I think in machine learning or deep learning, we have lots of models, right? From the simplest one to the complicated one. In general, we might have a better one. We have a good performance for our models. It could be complicated, okay? But if we say our model is good, that means we have some better performance than the other models, okay? But when you explain it, you must be very careful, okay? Whether the difference is big enough, or the difference just from the variance, okay? Even though the performance is good for your model, but if you consider the variance, it's not necessary to say your model is good, okay? So if we have a small difference on different models, and if you would like to select models, one is simple, the other is very complicated. In this case, I would suggest you to use the simple model instead, okay? Because there's not too much difference, because their variance is pretty small. If it is the case, try to use the simple model instead, okay? All right, so I think in a later course, in a later class, we might introduce some distributions, but not today, okay? And we have the centrality measures and the variance, and we can use these two property or these two numbers to describe the data set, okay? So we may use the mean or standard deviations. This is the most general way we describe the distribution of the data set. Okay, so this is why we need the descriptive statistics, okay? Here we just say the centrality and the variance. You might have other aggregates or the statistics like the maxima or minima, okay? Or the first quarter or the quartile, okay? So you can play around with that if you want, if you have the data set. Okay. All right, so I think, all right, are you hungry? All right, I will stop here today, and let's move on the discussion next Wednesday, okay? All right, so next Wednesday I will have, I will do a roll call because I do not know you so far, okay? I think after the registration for the course, I think I will do the roll calls next week, okay? All right, see you next Wednesday.